Okay, good afternoon. So just a couple of announcements. I know I've been bombarding you today with announcements, but it's been one thing after another. I'm sorry. So tomorrow, many of you might know, remember, is a national holiday in Denmark. So many things are going to be closed, including this building. But this room will be open, as will the revolving door close by. So that's the right way to enter the building. Simple things. Yes, so that's announcement number one. And announcement number two, very important, is that we are trying to create a list of accessible open problems, not like VP not equal to VP, but something that's more achievable. And as of now, we have how many?
2.
So, and it's me and Pratik that gave that to.
And one got resolved while I was writing it.
So we need your help. Thanks.
So welcome to the last session of the day. First talk is by Lee Volk on finding elements of large order modulo a given integer. So this is applications in linear factorization, and then we will talk about his recent work on finding deterministic algorithms of this problem.
All right, yeah, thank you. Thank you for coming.
So one more thing,
Oh.
if you want to ask a question, just ask on the mic if possible. If not, then we'll need to repeat the question. But it's preferable if you ask the question on the mic.
Okay, yeah, so I want to start with the integer factorization problem, which you've probably heard of. The input is an integer n, and the output is to find divisor of n, a non-trivial divisor, which is not 1 or n. Maybe you're a little bit worried, maybe you want to get the entire prime factorization of n, but you can notice that if you can solve this problem, then you can get the entire prime factorization just by, let's say you find a factor of k, so you recurse on k and n over k, and pretty quickly you recover all prime factors of n. So it's really much simpler and a bit cleaner to think about this problem. You just need to find some non-trivial factor of n. I would also have you noticed that, I mean, it's a trivial observation, but just to make things a bit clear, the input size is log n, the number of bits we need to write n. So when we talk about solving this quickly, we mean with respect to log n, right? A polynomial time algorithm would be an algorithm polynomial in log n. And it's a very important problem, right? I probably don't need to hype it up. We all know it, and we all bet our entire money on the fact that this problem is not efficiently solvable. But it has non-trivial algorithms, which is a bit worrying. And it's also a problem, and I will soon show you the exact results, where the best known randomized algorithms are much quicker than the best known deterministic algorithms. So from a de-randomization point of view, it makes sense to try to study what can we do deterministically. One last comment maybe is that I focus on classical algorithm, meaning not quantum, and algorithms that we can actually prove things about them. So again, not quantum algorithm and not heuristic algorithms. Of course, if you have a quantum computer, you can factor integers in polynomial time. You all know Shor's algorithm. In heuristic algorithms, I have nothing against them, but it's not the focus of this talk. Great. So how fast can we factor integers? If you want a randomized algorithm, or if you are willing to settle for randomized algorithms, there are actually sub-exponential time algorithms. So the first one of those, I think, was by Dixon, who gave an algorithm that runs in time roughly exponential in square root log n. So log n, I will remind you, is the input length, right? So this is not exponential in the input length, it's exponential in square root of the input length. There are some constant and tildes, but I think it's best to think about it like this. There are faster algorithms, especially if you want to factor things in practice. For example, okay, there are even faster algorithms again, which we can't really formally prove. There's also this algorithm by Lenstra and Pomeras, which looks, well, it's a similar expression. The constants are smaller. It's very easy to hide constants under big O, right? But they do matter, especially if they're in the exponent. So this is a faster algorithm. But if we try to use deterministic algorithms, then we actually have much worse results. So, okay, anyone can factor integers in square root n times, right? You just check all numbers up to square root n. This little of 1 accounts for the time that you actually need to do the arithmetic. So this is trivial algorithm. And then in the 70s, Lehman gave an algorithm that runs in time, well, instead of n to the 1/2, n to the 1/3. So again, it's exponential. It's 2 to the 1/3 log n, right? It's exponential in the input length, but it's better than the trivial algorithm. And this was quickly improved. Two different algorithms that are I mean, different but very similar, by one by Pollard, one by Strassen. It's sort of a baby step, giant step thing, if you know what that means. If you don't, then it doesn't matter for now. And we use FFT to speed it up. So you get n to the 1/4. And this has been the best deterministic algorithms for many years, even many decades, one could say, until a few years ago. There was a breakthrough, and Hittmeir found the deterministic algorithm that runs in time n to the 2/9, but then quickly after, Harvey improved it a bit and got an algorithm that runs in time n to the 1/5. Okay, so currently this is the best algorithms, best deterministic algorithms that we know of. If I have time, I hope to get to telling you a little bit about how these algorithms look like, because they're really interesting. It somehow combines this 1/3 and 1/4, and when you add 1/3 and 1/4, you get 1/5, right? As we all know. One key thing that these algorithms need is to find an element that has a large multiplicative order. And they need an element. I mean, here large means it means about n to the 1/5, so it's a good thing to have in mind if you're looking for specific parameters. Again, just to make sure that we are on the same page, Z star n is the multiplicative group, of elements, multiplication modulo n. So it's elements that are co-prime to n, and we multiply them modulo n. And the order of an element is the least power other than 0, I suppose, that you raise it and you get 1. So the order of 2 modulo 15 is 4, because 2 to the power 4 is 1 modulo 15, but it's not true for any smaller positive power of 2. Oh, yeah, I have it on the slides. Okay, good. So there isn't always an element of large order. Sometimes there are integers where the orders of all elements are very small. So it's almost polynomial in log n, right? It's log n to the log n. There's this joke, right, about the drowning number theories that goes log. So these numbers are okay. So we cannot always hope to find an element of large order. But if we are looking to factor integers, these numbers turned out to be easy to factors for unrelated reason. So they just have very small prime factors, so you can sort of efficiently find them. And so we are not too worried about the fact that sometimes we can't find an element of large order. Really, the setting you should have in mind that the number is semi-prime. It is p times q, and p of q are sort of large numbers, so about square root n. Right? This is the most difficult case, and it's really, well, we know like RSA encryption, for example, uses this setting, but also in algorithms, this is really the hardest case. And we can sort of reduce to this case in deterministic, not polynomial time, but much quicker than we know how to factor these numbers. So this is really without loss of generality. This is the case that we want to solve. And here, a random element would have a pretty large order. So it really becomes a pseudo-randomness question, right? Most elements have a very large order, but we want to find some element that has a large order, and we want to do it deterministically, right? Not just to pick an element at random. And again, this problem, well, it was needed to be solved for these factorization algorithms. So Hittmeir found an algorithm. He gave a deterministic algorithm. It gets as an input n and the target order d that you are trying to get. And d needs to be pretty large here, so at least n to the 2/5. And it either finds an element whose order is at least d, or it finds some non-trivial factor of n. Or it says that n is prime, okay? But let's not worry about prime numbers. Let's assume our input is a composite number. So, okay, we said we cannot always hope to get an element of large order, so we might accidentally factor n, right? But that's also cool, right? We accidentally solved the problem we started from, so we are happy with that as well. And I didn't say, and the running time is square root of t, okay? So, again, so, if d is, let's say, n to the 2/5, the running time is n to the 1/5. So, again, in terms of getting to our n to the 1/5 factorization algorithm, this is fine. It also gets you an element of much larger order than you need. You need n to the 1/5, you get n to the 2/5, so you get more than you asked for, and you have to spend quite some time doing it. So what we did is we improved this algorithm. We gave an algorithm that gets you the same guarantees, but it works for larger ranges of d. You can get all the way to d being n to the 1/6. Okay, so it's particularly useful again for this factorization algorithm where you need an element of order around n to the 1/5. Now you can do it much more quickly. Of course, we started this project trying to improve everything, but we cannot yet. So we sort of got stuck here. So let me maybe just restate my claim that there is a deterministic algorithm that gets an input n and gets, again, this target order d, which is at least n to the 1/6, and it either finds an element of order at least d, or it finds you a non-trivial factor of n, or it says n is prime. Okay, and the running time is the same, square root d. Yeah, Rafael, maybe you have us instructed to wait, yeah.
So, and this, but I guess, like, so if you know that, if you assume the generalized agreement hypothesis, then you can find in the first log, like.
I think so, yes. But I said I don't want to assume things, right? I want to prove, if you are willing to prove the general Riemann hypothesis. But I think something of that sort should be true, I believe, yes.
But you want to just, without any.
Yes, without any assumptions. Okay, here is I will tell you how the algorithm looks like. Okay, you get n, and this is what you want to find. And you sort of try to do a brute force search, right? You just try the elements one by one. And for each one you check, right? You first check if the order is at least d, and if so, you return it. You found what you needed. Otherwise, you actually compute the order of this number. And the order of an element, modulo n, it tells you some information about the prime factorization of n, right? It tells you the order must divide phi of n, the Euler-Toitier functions of n, which is the order of the multiplicative group. So it tells you some information about the prime factors of n, in some sense. And it turns out that after you try enough candidates, either, again, you find a solution to your problem, or you find a factor of n. Or you get enough information about the prime factors of n so you can factor n faster than you would be able to in general. So again, I'm omitting many details. It's not even clear, I guess, how to I mean, it's not difficult, but it's not a priori clear how to check that the order is at least d in times when you only have times square root d, right? You can't afford to compute all the powers, but this can be done, and I think the more interesting part is I think, in my opinion, is the last part. What type of information you learn about the prime factors and how do you factor? Yes, Newton.
Okay, so
It's not on, it's on top.
I thought you were on.
In the middle. In the middle.
It's near where your it's your
sorry. No, I don't know what it is.
you can repeat the question.
Oh, they're bringing the other one.
Sorry.
You can understand that he can repeat it.
Okay, I think the question is not
Too late. Too late.
You're committed, yeah.
somehow then checking whether order is at least is an easier question than computing the order itself somehow. Is that what you're
So it turns out it's the same thing, sort of. You can, there's one algorithm that checks if the order is at least d, and if it is, it tells you the order is at least d, and if it's not, it tells you what is the order, and the running time of this algorithm is square root d. And again, if I had extra 5 minutes, I could have shown you this. It's a simple algorithm. It's called Shank's algorithm. It's a classical thing, again, from the 70s. Another question.
Just shout. There's no reason to have a lower bound on d for this sort of a statement to be true, right?
For which statement?
If you want to find an element of order d, in principle, there could
Oh,
be
yes. So, okay, I will repeat the question. Yeah, Minan says there's no reason to expect a lower bound or d for this type of question to be true. And you are correct. Wait a few slides and you will be proved correct. Okay, so, but again, let's focus on the last part for a second. So again, like I told you, I tried to convince you that knowing the order of an element gives you some information about the prime factors. And the exact information that we get is on residue classes of the prime factors modulo some large number. So we get some number, which I called S, which is at least D, such that all the prime factors of N are 1 modulo S. Okay, so in some sense, we have eliminated 1 over S of the search space. We have focused on 1 over S of the search space, right? We have eliminated all other residue classes. Okay, maybe I should say it again. So we know that all prime factors are 1 modulo this large number S. And here it turns out this is a problem people have actually studied. So there is a theorem of Lenstra, which was then reproved by Kopperschmidt et al. And it says that if you have such number S that is coprime to N, and it is large enough with respect to N, so N cannot have too many divisors that equal 1 modulo S, only a constant number of divisors. In our case, again, we only assumed we have large prime factors, so the total number of divisors is constant anyway. So it's interesting in general. In our case, it's not so interesting, but what is interesting is that there's actually a polynomial time algorithm to find these prime factors. Okay, so maybe I should state it again. In general, for a number n, it could have many divisors, but somehow they cannot all concentrate on the same residue class modulo S if S is large enough. Only a constant number of them can fall in.
You're given n and S? Are you given n and S in this algorithm?
Yes. Yes, and there's an algorithm that you get n and s, and you find all. It is able to recover all such prime factors. And there's nothing special about 1. It's true for any residue class. Maybe I should state a reasonable open problem. So you can prove it for S, which is at least n to the 1/4, or 1/4 plus epsilon. One could make some heuristic argument that it seems like it might be true for every S, which is at least n to the epsilon. I think even Lenstra conjectured that it should be true. Yeah, we cannot prove it. And again, this algorithm is clever, but not difficult to understand. It's only, it uses elementary methods. Yes, there's a question.
So does it? This algorithm always find always find the divisors, or it can return also that there are none?
Well, if there are none, it will return there are none. It will find all those that equal 1 modulo S. Okay, great. So if S in our case was about D, the order we are trying to shoot for, so if D was at least n to the 1/4, we can just use this thing, but we sort of generalize it, and we can prove that if S is at least n to the alpha, for any constant alpha, or I guess alpha should be at most 4, then you can get a deterministic algorithm that does the same thing. And now the running time is n to the 1/4 minus alpha. So it sort of interpolates between the case alpha equals 4 until, well, as alpha gets smaller and smaller, the running time becomes larger, but also the guarantees are weaker. Right now, I mean, sort of, what was the question?
Sorry, alpha at most 4.
Oh, 1/4. Did I say 4? Well, just what I wrote doesn't make sense where alpha is greater than 1/4 because the running time should be a positive number.
Polynomial time algorithm?
No, the time is n to the 1/4 minus alpha.
Oh, okay.
Yes.
Oh, okay.
Yes. So again, it's sort of like I said, it gives you it basically takes this factorization algorithm that runs in time n to the 1/4, and it gets a 1/s acceleration over that, which is again what we sort of expected to happen. It's one of the rare cases in life where what you expect actually ends up happening. So just you play with the numbers and you see that if D is at least n to the 1/6, this running time is square root of D. Okay. Okay, I will quickly tell you how does this algorithm work, or a special case of how this algorithm works. So let's suppose we have a divisor of n, which is 1 modulo S. So, well, it's just S times x0 plus 1. And maybe a more convoluted way of saying the same thing, but it will pay off soon, is that this x0 is a root of this polynomial g of x modulo p0. Right? I'm just saying the same thing. But x0 is also a root of each of these polynomials. Can I use the mouse actually? Will it work? No, never mind. So it's a root of each of these. We can take power of g of x, and it will be root modulo the relevant power of p0. But we can also take power of n, because p0 divides n. So it will be a 0 of these polynomials, g to the x to the power j times n to the k minus j modulo p0 to the k for every j. So then it will be a 0 modulo this number for every linear combination, integer linear combinations of these polynomials. So really every polynomial in the lattice spanned by this polynomial. So now what you can do is to use the LLL basis reduction algorithm to find a short vector in this lattice, which will just be some non-zero polynomial that has small coefficient, And it's a linear combination of these polynomials that we started from. So the point here is that the coefficients of H are small numbers, and K is large enough such that P0 to the power K is a large number. So now let's assume X0 is also small. Okay, this is an unjustified assumption, but let's assume it for a second. So how can it be that you plug in a small number to a polynomial with small coefficients, right? And let's say it's so small that the absolute value of h to the x naught is less than p0 to the k. So the only way it can be 0 modulo p0 to the k is if it's actually the integer 0. Right? So you just solve this polynomial over the integers. And you get some number of solution, and you verify each solution. You try to see whether it actually gave you divisor of n. Right? This is the algorithm. You just find small roots and you check all of them. And this works as long as x0 is small. Okay? In general, it might not be small, so you just have to sort of shift the polynomials and run these algorithms over many intervals and do the calculation and see what you get. Okay, so now, yeah, here comes the breaking news that two follow-up papers, one by Harvey and Hittmeir and one by Nir, give an algorithm for the same problem, and it gives you the same running time, and it works for every d. So this answers my question. You don't have to assume now that d is large. We don't have uses yet for elements of very small order, but it's still a good thing to know that we can also find those pretty quickly. And it's the same general outline that we did, which is also the same general outline of Hittmeir's original algorithm. But the big improvements come from areas that I didn't discuss. It's not related to its problems of finding factors in residue classes. So yeah, you can just read those papers. Okay, I think I have like 5 minutes. So I will tell you very quickly about the n to the 1/5 factorization algorithm because it's interesting and obviously you all want to hear about it. So, okay, it's really going to be one slide. So let's start from the n to the 1/3 factorization algorithm. And again, suppose it's semi-prime. And suppose you have a good rational approximation of P over Q. So P over Q is a rational number, of course, but you can still hope for rational approximation with smaller numerator and denominator, right? This would be A over B. So, well, A over B is about P over Q, which means that by just multiplying it all out, AQ to the A times Q minus BP is small. And then you can notice this simple identity, which you just expand and see it. But what it means is that AQ plus BP is very close to the square root of 4ABN, right? And we know n, this is the input, and we know a and b. We sort of guess them or go over all options. So we can just search for a number which has the right form, AQ plus BP, around this square root 4ABN. Right? Just start from there and look for numbers in the vicinity that have this form. And if we have a candidate, it's also very easy to verify it's a good candidate because if you write down this polynomial, y squared minus c times y plus abn, the roots will be, assume if c is aq plus b times p, the roots will be aq and b times p. And this polynomial we can construct because, again, we know c is the candidate we are checking, we know a, b, and n. So this is Lehmann's algorithm. Again, you just have to feed in the right numbers to get n to the 1/3. So how do you get from this to n to the 1/5? What you notice is that alpha to the power of p equals alpha modulo p. Which means, again, by just using this identity, you get that alpha to the aq plus bp equals alpha to the an plus b modulo p. Or maybe a different, another way to write it is like this. So here again, the right-hand side is something that we know. And the left-hand side is alpha to some small integer, right? Because we said this, the AQ plus BP is very small to square root ABN. So we just look for small integers. We search for small candidates. We are alpha to the I, where I ranges over some set of small numbers. And we search for such collision. So again, if you are familiar with baby step, giant step terminology, like alpha to the I is the baby step and the right-hand side is the giant step. The only issue here is that we don't know P, right? Because that would be a factor of n. So we take a leap of faith and we say, well, maybe it equals modulo n, which is a stronger statement. And this is a win-win thing, because if it equals modulo, if we found a solution, then that's great. But if it doesn't, if it equals, it equals modulo P. If it equals modulo P and not equals modulo n, then we find a pair of numbers that equal modulo P and different modulo n, so their difference will be, the GCD of their difference with n will be non-trivial. So this is a win-win argument. But the point is, again, to do this argument, you need to start with to recover AQ and BP from this identity, you need to have alpha, a large order element. So I'm out of time, so I'll just flash out some open problem. One obvious open problem is to get a better deterministic factorization algorithm, maybe n to the 1/6. This is not just a numerology, right? Obviously, after we have 1/3, 1/4, 1/5, the next thing in the series is 1/6. But there's also a real sense in which the techniques we have today seem to maybe be able to get us to 1/6, but maybe to get beyond that, you would need new techniques. Of course, if you can do better, then that's even better. A related problem is to check for semi-primality. So one reason we maybe get stuck at n to the 1/6 is that even the reduction from general factorization to factoring semi-primes, if you want to do deterministically, then it takes time n to the 1/6. So if we can detect semi-prime numbers or factor semi-prime numbers better than n to the 1/6, it would be cool. And when n is a prime, the multiplicative group is actually cyclic. So you could hope to find a generator for the group. So the best algorithm I know to find a generator starts by factoring p minus 1, which would take you time p to the 1, O to the p to the 1/5, and continuing from there. So getting anything better than p to the 1/5 would be interesting. Yeah, all right, that's it.
Questions?
You were assuming a rational approximation A over B is given.
Okay, yes, or maybe actually I can just repeat it. Madhu was asking if I assuming the rational approximation over B is given. So no, I'm not assuming it. But the point is that because A and B are small, you can just search all candidates. But if you could do that part faster, somehow find the rational approximation faster, that would give an improvement.
Very nice. So, first of all, very nice. Your proof that you showed actually lines up, line by line, is a proof of what's called the Kopperschmidt method. So, I was wondering if you did it on purpose for everyone. You could actually use Kopperschmidt black box to get what you need, or you actually have to open it up and do it.
Yeah. So what he was saying is, yeah, maybe I should have mentioned it. What we did is it's very similar to an algorithm of Kopperschmidt that finds small roots of numbers of low-degree polynomials modulo composites. It's very similar, but it's not black box. You have to like fill it out with the parameters to make everything work.
More questions? Okay, if not, then thank you.